Hello, today I want to give you some idea about basic idea about Hermite polynomials. Generally in mathematics, Hermite polynomials are also called as orthogonal polynomials. Orthogonal polynomials. So generally Hermite polynomials are basically used in many fields. One of them are in numerical analysis. In numerical analysis as Gaussian quadrature. Gaussian quadrature, and in also in probability as Edgeworth series. Now Hermite polynomials are first in detail discussed by a scientist named Chebyshev. As his work was overlooked, again these Hermite polynomials are named after the other scientist whose name is Charles Hermite. He is the first person to define or to discuss about multidimensional polynomials. Multidimensional polynomials. So this is the basic introduction and basic idea of Hermite polynomials. Now what is the definition of Hermite polynomials? Generally Hermite polynomials are defined in two ways. They are probabilists Hermite polynomials and physicists Hermite polynomials. Generally probabilists Hermite polynomials are represented by Hen of x, and physicists Hermite polynomials are represented by Hn of x. This is given by the equation -1 whole power n e power minus x square by 2 into d power n, that is nth derivative of e power minus x square by 2, which can also be written as x minus d by dx of n in whole power n into 1. In the same way, physics Hermite polynomials are also given by equation -1 whole power n e power minus x square d power n, again it's nth derivative of e power minus x square, which is equal to 2x minus d by dx whole power n into 1. These are the two equations of probabilists and physicists Hermite polynomials. As we have seen here, these two equations are not at all identical, but these two equations are in one way these two equations are related to each other. That is Hn of x is equal to 2 power n by 2 into Hen of root x. This can be written in the other way as Hen of x is equal to 2 power minus n by 2 into Hn of x by root 2. In this way, these two polynomials, Hermite probabilists and physics polynomials are related to each other. Now the properties, now some of the probabilists Hermite polynomials are given by He0, that is 0th order of x is equal to 1. He1 of x is equal to x. He2 of x is equal to x square minus 1. In the same way, physicists Hermite polynomials are also given by H0 of x is equal to 1. H1 of x is equal to 2x. H2 of x is equal to 4 into x square minus 2. Now the properties of these two types of Hermite polynomials is that for probabilists polynomial, the leading coefficient, that is leading coefficient of the equation is 1, and for physicists the leading coefficient is given by 2 power n. This is the basic difference between probabilists and physicists Hermite polynomials. Now coming to these probabilists and physics Hermite polynomials are the solutions of a second degree differential equation, which is called Hermite differential equation, that is given by e power minus x square by 2 into u dash whole dash plus lambda into e power minus x square by 2 into u is equal to 0. This is second degree differential equation, which is called Hermite's differential equation. Hermite differential equation. So this differential equation has some constraints. Lambda should always be a non-negative integer, and u should be a polynomial which is bounded at infinity. which is bounded at infinity. These two are the constraints of this equation. Now coming to the recursive relation of these two polynomials. Now the recursive relation of these polynomials, Probabilist and Hermite, physicists Hermite polynomials are, for probabilist the recursive relation is given by hen plus 1 of x is equal to x into hen of x minus hen of x. This is for probabilists. And for physicists it is given by hn plus 1 of x is equal to 2x into hn plus 1 of x minus hn of x. So these two are recursive relations given by probabilists and for probabilists and physicists Hermite polynomials. Now we can also find some of the special values of probabilists and physicists Hermite polynomials. Now the polynomials evaluated at argument 0 are called Hermite numbers. So some of the special values for probabilists are hen of 0 is equal to 0 for n is odd, if n is odd, and it is minus 1 whole power n by 2 into n minus 1 factorial when n is even. In the same way for physicists it is given as hn of 0 is equal to 0 if n is odd, and minus 1 whole power n by 2 into 2 power n by 2 into n minus 1 factorial when n is even. So this is the basic idea of Hermite polynomials that I want to give to you. So that is end. Now I'll explain you about some Laguerre polynomials. Laguerre polynomials are similar to Hermite polynomials in some cases. First of all, Laguerre polynomials are given, they are named after the scientist called Edmond Laguerre. Laguerre polynomials are the solutions of the second order linear differential equation, which is given by xy double dash plus 1 minus x into y dash plus ny is equal to 0. Solutions of this are Laguerre polynomials. Solutions are singular only when these when n is a non-negative integer, that is n greater than or equal to 0. Now Laguerre polynomials are also, as Hermite polynomials, Laguerre polynomials are also used in numerical analysis, like in the form f of x in integral 0 to infinity f of x into e power minus x dx. Now Laguerre polynomials are represented by ln of x, which is given by the equation this way: nth derivative of e power minus x power n, which can also be written as 1 by n factorial into d by dx minus 1 whole power n into x power n. Some of the Laguerre polynomials are L of 0 of x is equal to 1, L1 of x is equal to 1 minus x. In this way, so these two are needed to find the recursive definition of the Laguerre polynomials. So recursive definition is given by Lk plus 1 of x is equal to 2k plus 1 minus x into Lk of x minus k into Lx minus 1 of Lk minus 1 of x by k plus 1. So for this, these two are needed, and this is the recursive definition only when k is greater than or equal to 1. This is the condition that should be remembered. K should be greater than or equal to 1. The generalized Laguerre polynomials are the solution of the generalized equation that is given by this equation. It is somewhat similar to the normal equation which we have written here, and alpha is real, some real value of alpha. So solutions of this equation is generalized Laguerre polynomials or associated Laguerre polynomials. And as I told you before, Laguerre polynomials and Hermite polynomials are related in some way. So the relation between the Laguerre and Hermite polynomials are given in this way: h2n of x is equal to minus 1 of whole power n 2 power 2n into n factorial into ln whole power minus 1 by 2 into x of x square. This is one relation. Other one can also be written as h2n plus 1 of x is equal to minus 1 whole power n 2 power 2n n plus 1 n factorial ln whole power 1 by 2 of x square. This is the other relation. We know that hn of x is a Hermite polynomial and ln of x is a Laguerre polynomial. This is the relation between Hermite and Laguerre polynomials. So in this way, Laguerre and Hermite polynomials are related to each other. That is the discussion about Legler polynomials. Now I'll explain you about moment of inertia matrix. Now let capital L be the angular momentum of the rigid body. This can be found by summation of angular momentums of individual particles on a rigid body. Now this angular momentum, we know that it can be given by Ri bar cross m into Vi bar, where m Vi bar is linear momentum of particle. Now, Ri bar can be written as matrix Xi, Yi, Zi, and Vi. Now, this can be written as M into into omega bar cross Ri bar, where omega is here angular velocity of the body, angular velocity of rigid body. Now this can be written as mi into summation of Ri bar cross omega bar cross Ri bar. Now first we'll evaluate this thing. This can be evaluated as in this way: omega x, omega y, omega z, xi, yi, zi. This, after solving this, we'll get it as in a matrix form. We'll get it as omega I zi minus omega z yi, omega z xi minus omega x zi, omega x yi minus omega y xi. Now again, by substituting Ri in this matrix, in this Ri, omega here is omega x, omega y, omega z. By substituting everything, we'll get the final answer as omega x into yi square zi square minus omega y xi yi minus omega z xi zi minus omega x yi xi plus omega y into zi square plus xi square minus omega z into yi zi minus omega x zi xi minus omega y zi yi plus omega z xi square yi square. This is the final matrix. This can also be written as sigma mi into yi square plus zi square minus mi xi yi minus sigma I mi xi zi minus sigma I mi yi xi sigma I mi zi square plus xi square minus sigma mi yi zi minus sigma mi zi xi minus sigma I mi zi yi sigma I mi xi square plus yi square into omega matrix, that is omega x, omega y and omega z. From this can be, suppose if ix is xx is equal to into yi square plus zi square and ixy is equal to yx is equal to minus mi xi yi. In the same way, ixz is equal to izx is equal to minus mi xi zi. Iyz is equal to izy is equal to minus mi yi zi, and iyy is equal to mi zi square plus xi square. Izz is equal to mi xi square plus. So from this matrix, I am writing these each element as in this way. So this matrix looks like capital L is equal to ixx, ixy, ixz, iyx, iyy, iyz. Again, izx, izy, izz into omega x, omega y, omega z. Now this looks like I omega form. So L is in the form of I omega. This matrix I, capital I, is called moment of inertia matrix. Is moment of inertia matrix. And elements in this, that is ixx, iyy, izz, these three elements are diagonal elements. These three elements are called moments of inertia. Moments of inertia. all the rest of the element, that is ix, y, iyx, izx, etc., all other elements are called products of inertia. Products of inertia. So this capital I matrix is called moment of inertia matrix, and this matrix is symmetric. As we see, this is equal to this is equal to this. So this matrix is symmetric. So this is called moment of inertia matrix. I want to explain you about rocket dynamics using Hamiltonian and Lagrangian mechanics. Take an earth, this is an earth, and rocket is going up. Rocket has mass m at that instance, and the distance between the rocket and the earth is, let it taken as q. Q is, we know that it is generalized Cartesian coordinate, and q dot is a generalized velocity of the body, that is rocket. Now the kinetic energy of the rocket is given by half m q square, and potential energy is given by mgq. Now we know that according to the Lagrangian, L is equal to k minus u, which is a constant. This is half m into q dot square minus mgq. Now we know that Lagrangian equation is given by d by dt of dou L by dou Q dot minus dou L by dou Q is equal to 0. This is the Lagrangian equation. Now I'll substitute this L in this equation. Then I'll get dou L by dou Q dot as mq dot, dou L by dou Q as minus mg. And by simplifying this equation, we'll get, by substituting this in the above equation, we'll get in this way. And the simplified equation is this. Here m is variable, because as rocket is going up, mass will be decreasing, so m is a variable. So I am using this here, and this is the final equation of motion which I have got from Lagrangian mechanics. In the same way, I want to show you the same thing using Hamiltonian mechanics. So in this Hamiltonian, h is equal to k plus u. We know that this is the constant energy. This is total energy which is constant for isolated body, and this is half m q dot square plus mgq. And we know that Hamiltonian equation, differential equation, is given by this: dp by dt is equal to minus dou h by dou q. Now p is equal to dou L by dou Q dot, which is a momentum. This is called momentum of a body. So from Hamiltonian equation, which is this, from Hamiltonian equation, we get d by dt of mq dot is equal to minus dou h by dou q, which is minus mg. This is mq double dot by dm by dt is equal to minus mg. This is again the equation of motion that we have got from Hamiltonian mechanics. So actually we have to get the same equation for Hamiltonian and Lagrangian. So here this is the Lagrangian equation. Like from Lagrangian equation mechanics we got this equation, and from Hamiltonian we got this equation. So these two are equal. So hence it is proved. So the equation of motion of the rocket using these equations, these mechanics, is given by this. This is the final equation of motion. So this is proved.